Okay, in this problem, we're asked to find the derivative of y with implicit differentiation. So we have to take the derivative with respect to x of each of these sides, and we'll handle them both separately. But let's see the tricks for doing it. So let's just deal with the right-hand side first for a moment. What is the derivative of x to the x? How do we even figure it out? It is certainly not just x minus 1 times x or something. That doesn't work. It's actually a lot more complicated than that. So here's the common trick. First of all, let f be any function at all. F of x is just some function. And suppose instead of computing its derivative, I'm interested in first taking the logarithm of it and then computing the derivative of that. So at first this seems like a very silly trick. But watch what would happen. F is any function. I can't be too specific, but I can say by the chain rule, since I know the derivative of ln of x is 1 over x, this is going to be 1 over, and then you plug in the inside, and then you multiply by the derivative of whatever's inside, which is just f prime of x. I can't be more specific because I don't know what f actually looks like. Or in other words, multiplying both sides by f of x, f prime of x is just itself, the original f, times the derivative of the natural log of f of x. So it seems like we've made things substantially complicated, but this is a trick called logarithmic differentiation. Because sometimes it's easier to compute the derivative of the logarithm of the function you're interested in than the function itself. And this is a perfect example of that. So by logarithmic differentiation, if we let f of x equal x to the x, then this would just be f prime, and apparently that's equal to the original f of x times the derivative of the logarithm of f. So I'll actually write it out. The original f is x to the x times the derivative of the logarithm of x to the x. Now, is it really any easier to compute the derivative of the logarithm of x to the x? Let me switch colors. The answer is yes, because the logarithm of x to the x, now this is just algebra, the x can come out, is the same as x times ln of x. So now, if you computed the derivative of this, that would be the same as computing the derivative of this, because they're equal algebraically. But this is easy to compute the derivative of. It's the product rule. It's the derivative of the first thing, which is 1 times the second thing, plus the derivative of the second thing times the first thing. Well, the derivative of ln of x is 1 over x times x. These guys will cancel, and that's just 1, so that's just ln of x plus 1. So this thing here is actually, well, what we just figured out, ln of x plus 1. So the derivative of the right-hand side is x to the x times the quantity ln of x plus 1. So I'll write it here in blue. Its derivative becomes this. We can also, and I'll switch colors again, we can do something similar with the right-hand side, with the left-hand side, sorry. Now, our f would equal 5 to the y cubed plus y squared. And so f prime would equal what? Well, I mean, here we have a bit of a situation because the y's are themselves functions of x. So we're going to have to use the chain rule. So I could use logarithmic differentiation, or, if you don't mind, I'm going to do something what I consider to be a little bit easier, a little less confusing than logarithmic differentiation. We had no option but to use this logarithmic differentiation trick here on the right-hand side, but we have other options here. So let me ask you this question. We know what the derivative of e to the x is. It's just its own derivative. But what if I had something like 5 to the x, because that's more relevant to the problem at hand? What is its derivative? Well, there's actually a very common trick. Do you notice that if we take ln of 5 to the x, and then we exponentiate that, the e cancels with the ln, and that is just 5 to the x. So it's silly. I do something and then I undo it. But now I can use a property of logarithm that these exponents come out in front. That's just e to the x times ln of 5. And ln of 5, it's not a number that I can write down off the top of my head, but it is just a number. It is just a constant. So we really have something of the form e to the kx, where k is a constant, and the derivative of that is easy by the chain rule. It's just e to the kx times that constant k. We're just using the chain rule. So, in other words, the derivative of e to the x ln of 5 by the chain rule is just ln of 5, the constant comes out, times e to the x ln of 5. So sorry, what is that? That's not equal to it. That's the derivative. Alright? So ln of 5 e to the x ln of 5 is the derivative of this, which is equal to this, which is equal to the original 5 to the x. But again, remember, e to the x ln of 5, you can bring the x back up now and then cancel the ln with the e, so that's just ln of 5 times 5 to the x. E to the x ln of 5 was equal to 5 to the x, and that's all I'm doing here. I'm just replacing it back. So when you have something other than e to the x, you have some other base to the x power, and you want to compute its derivative, then it just stays the same, just like with e to the x, except you have to multiply by this factor of ln of whatever that base is. So long story short, the derivative of 5 to the x is ln of 5 times 5 to the x. So now that we have that in our back pocket, we can compute the derivative of the left-hand side with respect to x simply using the chain rule and implicit differentiation. So what does this turn into? I'll put it down here. This is just ln of 5 times 5y cubed plus y squared. It's as if you just take the derivative with respect to whatever's in top. Except now, by chain rule, you have to multiply by the derivative of whatever's up there in the exponent. So we have to multiply by that. Or ln of 5 times 5y cubed plus y squared. What is the derivative of y cubed plus y squared? Well, by implicit differentiation, or by the chain rule, whatever you want to think about it, it's 3y squared plus 2y. You just take the derivative as if you're taking the derivative with respect to y, but then you have to multiply by y prime, right? To multiply by the derivative of the inside. So the left-hand side should equal this, the right-hand side should equal this, and I'll leave it to you to simply divide both sides by this quantity and solve for what y prime is. But that's the trick there.